All right. I'll also mention here something else. When AFNI itself starts, you'll notice there's a brief image that shows up in a picture, and that, along with things like the startup tip, that picture that goes by so quickly nowadays it's called the startup image, or a face image, and those are all images that users have provided. And so the idea was, when AFNI first started and things were slower to load, that gave you something to kind of look at or tell you that it was working. And so there's an image of a user, and then also some kind of background image. And actually, if you right click on this AFNI GUI image here, you get a menu of different things here. So one, it's important you can always read the US Constitution. That is embedded in AFNI. You can read Declaration of Independence. You can pick a sonnet, or have a random sonnet chosen for you by William Shakespeare. So this will surely help your brain imaging studies. And then the AFNI faces here, I think these will go by rather quickly, but these are all the AFNI user faces. So I have to close it to make it go away. Anyways, if you want to, you as AFNI users can submit your own photo. It gets downsampled to 128 by 128 pixels. But anyways, it's kind of a fun thing. Speaking of fun, let's talk about dataset alignment. So I'm going to CD into AFNI handouts. And inside here, I'm going to AFNI open oops, if I spell it correctly, AFNI 14 presentation on alignment. You can open up the PDF version like this. I'm actually going to open up the LibreOffice version I have, because there are a couple movies on it. So I'm going to do something different than that command, but you can AFNI open AFNI 14. Let's talk about various forms of alignment. Again, a lot of abbreviations just for reference. So what are we trying to do here? We have different data sets of different kinds, and we're trying to bring two data sets into correspondence, so that from a volumetric point of view, if I click on a certain location, or if I overlay them, that I'm hoping that they are in the same space, so that location by location, the two objects correspond with each other. So some programs call this normalization. That's fine. Maybe call it spatial normalization, but since normalization can mean many things, we try to avoid that. We use terms like registration, co-registration, alignment in various forms instead. There are a huge number of cases where we'll use alignment, and it's good to know about what our data sets are and what we're trying to accomplish in each case. So we've talked about several of these already from the morning. Motion correction, or the process of estimating motion, is EPI to EPI alignment. The EPI, the fMRI volume at time 27 and 31, and aligning those together and seeing how far off they are. EPI anatomical alignment, we're taking a subject's own fMRI data that can be a little distorted and may not have the clearest features, and we want to align it to that subject's own anatomical to help unwarp it a little bit, help know better where the locations of the brain are, see where we've lost signal, all sorts of things like that. Anatomical to template alignment, everybody's brain is different structurally, and so it can help us to perform group statistics if we can make everything fit onto the same bumps and wiggles of a sulci and gyri of a standard template. And so there's even other things. We can use distortion correction, sometimes just for visualization, what we call axialization, or what is sometimes ACPC alignment. This is its kind of cousin that's a little more hands-off to do it. And even for quality control, we'll use alignment. So these are all very different purposes and very different kinds of data and very different needs. So we'll go through general alignment terminology and then go through each of those cases. In general, we're going to want to know what we're doing for the purpose of choosing a particular program and some of the options that will be most suitable for performing that kind of alignment. So we want to know what is the purpose of it. Are we trying to undo distortion, or are volumes good volumes? Or is it the same subject, or is it two different subject volumes that we're aligning? Do our data sets look very similar, or are they different? Sometimes we line data where the ventricles are bright, where to data where the ventricles are dark. And so we have to know about that to tell our program to match those things up. Sometimes we have very different field of view coverage, skull on, skull off, all sorts of different considerations that can affect the options, which is why we have so many different programs and options, because people have so much different kinds of data. And so we're going to talk about a few of the keywords in this. Again, not everyone comes from a data processing or computational background, but it helps to know these things, certainly for kind of asking questions and reading help files, and maybe it's fun as well. Many of the details will be taken care of within AFNIPROC, but it's good to know about the options and what you're selecting and why, how to judge the quality of how things went. So it still is good to follow along. Don't fall asleep, please. Okay, so let's talk about important concepts like tissue contrast. So when we look at these three volumes here, which ones have similar tissue contrast to each other? So out of these three volumes, which have similar tissue contrast? Okay, take a look and decide. For me, it is A and C that have similar contrast. Now, they have other properties that differ, but the ventricles are bright here and they're bright here. And then the gray matter is the next brightest thing. And we see around the edge, gray matter is kind of bright and the white matter is the darkest. So that's the tissue contrast property that we're looking at here. Here, the ventricles are dark and the white matter is the brightest. So that's different, or even in this case, opposite tissue contrast. This is important so we know what cost function we use, and we'll see cost function is the thing that drives goodness of matching in the algorithm. So it's a really important property to know. And in terms of spatial resolution, another property, which kind of data sets here have high resolution, would you say? This one is probably pretty clear. Literally clear with the higher resolution data sets. We see nice sharp edges, nice sharp features, and the voxel sizes are smaller, so the data looks smoother. This continuum here, and this looks kind of chunky in early 80s Nintendo, which is great. It's the best time to play video games, but anyways, this is just lower resolution data set. This may affect which data set we choose as the source data set or the base, which one we're warping to and from. Other considerations come into that as well, but it's good to know. Field of view coverage is another important one. Are we including the whole brain and in both data sets? So again, in here, which data sets have basically whole brain field of view coverage? These two data sets do, I can see very clearly space above the top of the brain and below the cerebellum here, whereas here, even the top of the brain is essentially cut off, and usually we don't want data we care about to be on the very edge, as it were, of the field of view, because the data quality is going to be poor, and certainly the cerebellum is cut off here. So this data is probably not the highest quality, and obviously we're missing part of the brain there. So anyways, it's good to know, and also sets our expectations of overlap and what we think we care about and need to work to match well. And just a super important one is often when alignment fails or something, we're going to ask how much did the data sets overlap in the beginning? How far apart were they? How much work did we have to do to get them to line up? And there are a couple different ways that data could be close or far. So if we look at these, we'd say that these data sets here have a large rotational difference between them. It's easiest to see in the axial view here. The grayscale underlay is kind of up and down like this. That same axis is about 45 degrees away. That's a large rotation to try to overcome for the algorithm. It might be able to, but it's just going to make it a little bit harder to start, and we want to be aware of that. This is a large translational difference. The center of mass, or the amount of just general overlap, is quite poor to start. And these two for starting are pretty darn close. And anything that we can do to have them, the two data sets that we're going to align, start closer together, whether it's translation or rotation, things like that, we're going to be more confident, or we're going to have a better odds of having a good outcome with this. Each of these can probably be aligned. We can start with a center of mass step to try to do something quick to align these better. Rotation can be quite hard because we don't know the rotational difference to start. And we're worried that a different fit, we might get stuck in kind of a local minimum of poor fits where instead of unrotating the brain, it would just get geometrically squashed in one way, and the algorithm thinks it's doing a good job, but it was never close. So, anyways, these are the kind of things that we want to be aware of. And if we have to troubleshoot, this is always a good thing to kind of have as an image to check. How is alignment actually calculated? Well, across any algorithm we're going to talk about, this is basically the way it goes. So we take two images, a base, which is our reference, and a source, which is the one that's going to be adjusted and moved around some way. We start by quantifying how similar they are in some way. If they're similar enough, then we're going to stop. Like if they're aligned well, then we stop. Otherwise, we tweak or perturb the source image. We might rotate it, shift it, stretch it out in different ways. And then again, we quantify how similar the new source is to the base. And if it's similar enough, we stop. Otherwise, we tweak, and we just go through this again and again and again with various forms of fanciness added in. So the first part of it, how do we quantify how similar data sets are? That's the role of what we call a cost function. It's a mathematical rule, a function, that takes the base and the source data set, and it makes an overall assessment of how similar they are. So it does something multiplying across all voxels, comes up with a single number, and if that number is small or very negative, as it were, then we might be happy with it. And so what is the rule that we look at across all of them? Well, that's the kind of secret sauce of the cost function, and there are lots of different cost functions for different roles. Something we could do is reward similarity when peak values line up, and that would be good when we have matching tissue contrasts. So if the ventricles are bright in both our data sets and we want them to line up, we want to reward when bright things are matched up with bright things. But we could also reward when anti-peaks line up. So if we're aligning a data set where the ventricles are bright in one data set and they're dark in another, we might want to reward, that. And that's a very different rule between these that are going to drive either good or poor fits depending on the data. And there's lots of cost functions in AFNI for historical reasons and developmental improvements, and also kind of comparisons with what some other softwares have done that people have recommended. And we have this kind of cheat sheet for the most common cost functions that you're going to want to use in AFNI programs. So in general, I'll start with this one at the bottom. When you're doing EPI alignment, this kind of motion correction alignment with 3D Volreg, you can just use the default cost function, often called LS, which is a simple least squares, very fast to calculate, and you kind of never really have to change that in most cases. For most other times where you're doing alignment, if your two data sets have similar contrast, you use LPA or some variant of this. And if they have differing contrast, you use LPC. And the kind of variants that you might have are plus ZZ for a little extra stability. So it's slower, but usually it has less chance of something really weird happening. So if your data set has some noise or is starting off far, you might want this just to be a little more secure. So you're basically going to use LPC plus ZZ if you have differing contrasts, LPA or LPA plus ZZ if you have similar contrasts. If you have very, very weird data and none of these are working, then you by all means ask. The other kind of fallback one is this NMI, the normalized mutual information. But this is your cheat sheet for kind of similar or different contrast is going to set your cost function in most cases. And 3D Volreg, you can just use its default. All right. how do we know, A, how do we know what to recommend, and B, how do we check this out? Well, we're doing alignment, so we have an algorithm driving similarity, and it's using a rule of similarity to say when it's done a good job. So we can't use a cost function to determine it because it thinks it did a good job. We need to evaluate this visually and check and see that it did the right thing. So here's a case of how we like to look at overlap is with turning the edges, one data set into edges and the other one we see as an underlay. Because what it means to have a good alignment is not so much just the outer boundary, but actually all the features where the edges between tissues are. So the gray-white boundary, ventricle boundaries, um, sulcal, gyral features, and things like that. So we can see that overall, in terms of our start here, how well do our two data sets overlap to start? They overlap pretty well. It's not perfect, but I can see that the boundaries are pretty good. There doesn't seem to be a large rotational difference. Fine. If I use the cost ratio, the CR cost function to align them, I might think, well, the boundaries all look well aligned, so this must have done a good job, right? Well, but when I really look at the details of the features as the edges show me, it looks a bit messy and things aren't really lining up very well. So this cost function did something about alignment, but it didn't really do the job we wanted. Um, Even here, it looks kind of an odd alignment. If I use mutual information, then similar thing here. It's pretty good and the edges are good, but really the details inside here aren't that great. And when we come to the LPC, actually now we can see that actually a lot of the tissue boundaries align very well. So you don't see a lot of this kind of leftover mess. The ventricles are much better aligned, etc. This one actually got the features, and this is a local Pearson cost function, so it does a lot of local fits and accumulates those. So it should be paying attention to local features, even though it's a global fit. So anyways, these are the kinds of things that we've tested over time and the way we look at alignment and the way you should look at alignment too in your own processing. Okay, so that's about the cost function aspect and this tweaking and perturbing of the source data set. Well, how much are we going to tweak, perturb, change, allow our source data set to change? We quantify that in terms of what are called degrees of freedom. And so we can allow more kinds of changes by allowing more degrees of freedom to the algorithm. And the we know kind of a family or how many generally to allow based on the kind of alignment that we're doing and the kinds of data set that we have. There are a few kind of major categories of these. So I'm legally obligated to show a flow chart here because I mentioned kind of an algorithm, but I'm just going to skip over this because we've already covered it. In terms of the kinds of tweaks and perturbations that we can allow, the first family of them are what are called rigid body alignment. So these can overcome simple differences between data sets like rotation. So I take one data set and rotate it relative to the other, or translation. We live in a three-dimensional world, so I have three axes I could rotate or translate, which leads to a total of 6 degrees of freedom. This is the kind of alignment that 3D Volreg does. When we have someone in the scanner and they might be moving their head, we're mostly expecting that they're moving it by rotating it or translating it a little bit. We're not really expecting larger deviations of shape changes. This does not change anything. That's why it's called rigid body, because we're assuming that someone's head shape is not changing in the scanner. So this purpose matches this kind of expected amount of deviation across time, just rotations and translations. The next family of parameters with more degrees of freedom are what are called linear affine. So they still allow for rotational and translational differences, but now we allow the data sets to be scaled different. So either in all directions bigger, all directions smaller, or smaller and bigger in any kind of combination like this. The shearing motion is something like if you take a stack of printer paper and you unwrap it and you put your hand beneath it and on top of it, and then move your hands in opposite directions a little bit, that the way that your rectangle of paper moves into kind of a rhombus shape, that is the shearing motion. Now, this seems maybe a little bit funny. Well, why are we going to use this? We actually use this quite often when we align a subject's own EPI to their anatomical data set. Now, I just said we don't expect someone's brain to change in the scanner, but in this case, we're aligning an EPI data set that might be distorted geometrically in some of the ways we looked at earlier to an anatomical that we don't expect to be geometrically distorted. So while we're allowing for simple motion, we're also allowing for the practical reality of the EPI distortions relative to our anatomical data set. When we align EPIs to EPIs, we expect them to be all kind of distorted in the same way, so we don't need to allow for scaling and shearing like we would here. We have 3 degrees of rotation, translation, also 3 of scaling, and also 3 of shearing for a total of 12 degrees of freedom to fit. So when we're allowing our source data set to tweak and perturb in space, it's actually changing these different parameters and then trying to find throughout all the random 12-dimensional space of all combinations how our data sets fit together if we allow maybe a little bit of shearing and scaling, etc. The programs in AFNI that use this are 3D Alineate in particular and Align EPI and nat.py. As the name here suggests, this is specifically designed for aligning EPI to anatomical data sets. This is what AFNI Proc uses. It's actually a wrapper for 3D Alineate, where it's kind of preloaded with a lot of options and extra functionality for the specific use case of EPIs and anatomical data sets. And then finally, the next level up is a big change for how alignment works. Now we allow data sets not to just be a simple kind of global change of rotating the whole data set, but I allow a data set to rotate and part of it moves differently than another part. And so it kind of blobs around into what can be really quite weird distortions here that I've accentuated for the purpose of visualization. Hopefully this is not happening to much data in the scanner. But what this does is whenever we do nonlinear alignment, we start with a first pass of simpler affine alignment, so a global fit wherever the data set rotates or shears there. And then we zoom in on a little location and we allow this to refine itself. And then we go to a different location and allow it to refine independently, etc. And we keep going over smaller and smaller patches until we've made the whole thing match up better. So this allows for many, many, many degrees of freedom, hundreds or even thousands. As I said before, it starts with an initial 12 degree of freedom fit to get things close, and then it refines and refines and refines over multiple levels. It's much more computationally intensive. Several AFNI programs are inherently parallelized, and it's in particular a lot of the alignment ones are because they get to be more computationally hungry because they're doing all these subset calculations over your data. So 3D QWarp is the main workhorse, but we have these other wrappers, SS Warper or SS Warper 2, Animal Warper. This is what we'll basically use, or SS Warper 2 now, preparing for AFNI Proc, and this is what we would use for preparing for AFNI Proc when we have animal data specifically. So this is just a case to give us a sense, a little bit of the similarities and differences across all these cases of alignment. So this is taking the data set that we're going to look at tomorrow, the subject's anatomical, and aligning it with rigid alignment to the MNI template. And so what we're doing now is we're showing the underlay data set is the base, so that's the reference template, the MNI template, and the overlay is the warp data set here with just 6 degrees of freedom. You can see that it's probably apparent these data sets have been aligned. The boundaries mostly match, not perfectly because the brains just have different shapes, but some features match up. Okay. Now, if we allow for more degrees of freedom in the fit, as many as 12 degrees of freedom with affine, you see that things have gotten better. The shape is now allowed to fit a bit better, and I'm just going to go back and forth. So rigid and affine. And you can see that the boundary is now much better. The Selkai and Jaurai are probably better, but not great. And this is not exactly what we'd want for our real analysis. And if we now allow for full nonlinear alignment, you can see that things have cleared up quite a lot, particularly in this upper part of the cortex where individual brain differentiation differences are much greater than in the subcortical part. So um, the human brain is just going to look more similar here across subjects than up here across subjects. And so now if I go back and forth through these different degrees here, this is rigid, affine, nonlinear. And you see really the benefit of nonlinear locking in many, not necessarily every sulcus and gyrus, but really quite a lot of them. All right. So yes, anyways, this is the what we're trying to do with the alignment, and why when we're aligning different subjects to each other, we're almost always going to use nonlinear alignment. When we align different data sets of the same subject's brain among themselves, we use rigid or affine typically. But for subject to subject or subject to template, which is also subject to subject in a different name, we'll use nonlinear. All right, just a little bit more about this idea of transformation and mapping here. This is really what we're setting up when we do alignment. We're making a transformation between two data sets. We have a source, which is data somewhere on its own grid, and we have a base where the data might exist on its own grid. And I've tried to colorize here the fact that like this is a simple data set, and then this is that simple data set rotated, kind of this way, and then at a different resolution. And so when we're trying to generate a transformation, we're trying to say like for every voxel here in our base data set, where is the equivalent location in the source? So we often think about sending source information to the base, but in actuality, we should think about it like going to a centroid in the base and pulling information from somewhere in the source. And the rule for doing that across the full field of view of the data sets is the transformation, which itself is kind of a voxel-wise data set. So we have to remember that indeed our base is a grid that's sampled, and we have these centroids, and our source is also a grid, and it itself is made up of essentially a centroid that we kind of fill out here, and we colorize the whole voxel. Okay, so we think of this maybe as a continuum, but we have to remember it's actually discrete. So again, the way we should really think about alignment is go to my base data set, and I want to figure out where to pull information from my source. So for this centroid, the alignment algorithm figured out that it should come from here, this location. Okay. Now, if we think about that a little bit, what does it mean that information from here should get mapped here? Because this is not exactly on a centroid, it's near a boundary between a couple, and how do we want to figure out what is the number that should get pulled onto the base data set here? Well, the rule for figuring out how we choose to pull information from the source data set is what's called interpolation. So, excuse me, we could say, let me take kind of an average of the area around here weighted by distance from that point that I want to pull from. So maybe I should take an average of mostly these two voxels here with a little bit of these other ones, because the information is neither exactly this one nor exactly that one, and it's mostly that. So this would be a cubic polynomial. I've kind of weighted the coloration here by how the weighting would work for interpolating or averaging data. Okay. There are other kinds of interpolants we could use. Through the magic of signal processing, this one called WSync, which actually in a 2D slice looks like this wiggle up and down and has some negatives in it. This preserves edges better than this one. So this one, when I use it, will make a kind of smoother, blurred representation. This one will as well, but it will be more edge preserving. And then sometimes I have data that it doesn't make sense to average across. Like if I have a data set that's integer valued map of an ROI, it doesn't make sense to average region 4 with average region of 13. The result of that average 8.5 is not a real region, and it wouldn't make sense. So for that, we have what's called nearest neighbor interpolation. So I'm only going to pick from whatever voxel square I fall into and not average across anything. So this is useful when I'm interpolating atlases or ROIs or masks. These are useful when I'm interpolating floating point valued data sets. Okay. And it's important to note the difference between estimating a transformation and applying a transformation. So when we want to estimate a transformation, we're going to use data sets that have kind of full anatomical information, like maybe we want to send this ROI map to this base space here. I can't just align this colorful ROI map to this one. I have to use a data set that's in its same space that has the kind of anatomical information and estimate the transformation from the source to the base space. Then I can apply it to any other data set in that source. So I'm going to estimate a transformation rule that for every voxel in this base data set, where would I pull information from the source? And then I can apply that rule with the correct interpolant to this ROI map. And so I estimate the transform and then I can apply it here. And I would choose, since this is an ROI atlas, I would choose the nearest neighbor interpolant because I don't want to average across things. And so this would be the way this maps over here. Now, when you look at this and you look at this, there might be some odd edge things that happen or a little bit of fuzziness. There are ways we can smooth out the edges around these as a separate step, but this is basically the way that we would estimate a transform between these and then apply it to other data sets, which is a very common thing. And it's important to note that we will often not only just apply a transform from data set A to B, but we're going to have several data sets like the EPI to the anatomical to the template. That's A to B to C. And what we could do is we could make a transformation from the EPI to the anatomical and get a new data set. And then between the anatomical and template, we have a transformation. And so we send that along there. There are different ways that we can do this. Like we have multiple transformations between our subject EPI. We align it to one for motion correction. We align it to the anatomical for better fiduciality, and we align the anatomical to the template to send it to template space. If I create a new data set every time I apply the transformation individually, that is going to accumulate a lot of blurring successively, because every time I apply a transform, I blur and regrid the data set because I'm always interpolating onto a new grid. And so that's possible to do, but what we want to do is use the mathematics of estimating each transformation individually, but before we start applying it successively, concatenate all the transforms so we just apply one giant omnibus transform to our raw data. That is going to be much happier for not blurring the data too much. So this is a case where in a processing pipeline, it's not that it's necessarily fully wrong to regrid the data multiple times, but it's going to be a non-ideal property because it's going to blur it in an uncontrolled way that we don't want. So this is one of the reasons why you kind of entrust your analysis to a pipeline program, because, for example, if you're using AFNIPROC, you can estimate all these transforms, concatenate them, and it will apply it correctly. That's what it's built to do for you. You can control all the options for how these work individually, but that's why it's nice to have a start to finish processing all in one place. Just as a side note, we often will not recommend upsampling the EPI data a huge amount. Some software have this by default. So let's say you acquire your data at 3.5 millimeters and it just upsamples it to 2 millimeters isotropic voxels by default. That's essentially multiplying your data set size by a factor of 8 or so. You can't really create higher resolution information, even though it will look nicer, and it will make a much larger data set with much more processing time using up much more disk space. So we often, between your raw data and your final template data, even if your template space is 1 millimeter, you don't have to send your EPI data to that higher resolution or anything near it. You can upsample it a little bit, and then go from there. And that's what we tend to do. If your data set is coarse when you acquire it, you can't magically make it high resolution just by upsampling. Okay, so I won't cover this. This is just a friendly cheat sheet for a lot of the things that I went through about some of the programs, the cost functions, and things like this, so that you can remember them. All right, so let's start talking about the first case of where we look at alignment. So within EPI alignment or EPI alignment. This is what we've talked about a little bit when we have subject motion in particular, whether it's human or non-human data. When I have different data sets at different times without motion, they look very similar from time point to time point. When I have motion in my data, what happens is either during the time a volume is acquired or between two volumes, although in reality it's kind of always during the acquisition of some volume, if the participant moves, because my data is acquired interleaved, I pick up these weird patterns here of this striping. So instead of acquiring a whole volume, poof, now, and then 2 seconds later, poof, another volume, I'm actually spending like 20 milliseconds acquiring a slice and then another 20 milliseconds acquiring another slice. And it's not even as simple as slice 0, 1, 2, 3, 4, 5. I actually acquire 0, 2, 4, 6, 8 all the way up and then go back and get 1, 3, 5, 7. In that way, I don't kind of pollute information across the signals as long as there's no subject motion. But all this is to say, when the subject moves, we see this weird stuff happen geometrically to the data set, and within the time series themselves, we start to pick up spikes or other features or baseline jumps that we looked at a little bit. So I'm just going to take a drink of water. Thank you. All right, so you can see the difference that happens here. What we want to do to first estimate the amount of motion and also to try to undo some of the effects of it is we're going to run 3D volreg. We're going to define one volume in our EPI time series as special and align every other volume to it. So that's EPI to EPI alignment. So across EPI time point, let's say 7 is special and everything is going to get aligned to it. The amount of, so we're going to choose, first of all, how much freedom are we going to allow for there to be in the alignment process? As we said before, just translation and rotation. It's this rigid body alignment. So we have 6 parameters, 3 translation, 3 rotation. The DP means along the anterior posterior axis, DL is along the left right, DS is inferior superior, yaw, pitch, and roll are nodding, shaking your head, and moving it left to right. And you can see that basically we're going to store the amount of change in anterior posterior translation all across time. So this axis is time. And so for time points where there was very little motion, any parameter, the change in it is kind of 0. What does it mean when we have this big change here? This is where there was a big change in position relatively. So wherever we see not necessarily a large value, but a large change in these values is where there was a large motion event. So actually, from here to here, there's very little change in DP. That means the person at time point, let's say 30, 31, and 32, had their head in the same position. It was equally the same from the reference point, but they weren't really moving it at this point. Then they started moving, and now they were pretty constant in this posterior anterior axis. Then they were moving again, etc. So it's the derivative of here that tells us when there was a large motion event. So there's actually not a lot of motion during this time because the alignment parameter is pretty constant. But then all of a sudden they start moving a bit and then constant and then moving, etc. Okay, so this is one way we can see how much motion there was and make a record of it. And by doing alignment, we're also kind of putting the brain back in place over time on a voxel by voxel basis. Another way we can look at this is what's called a gray plot. So we can see instead of here, we looked at the time series, and at every time series, we're seeing whether it's going up or down across time by looking at a line going up or down. And I can do that for 25 voxels pretty well. If I want to do that for all 60,000 voxels in the brain, it's pretty hard to do that as a matrix. A way I can accomplish it is to turn every voxel's changes into grayscale. So this is still the time axis. And what I'm doing is imagining like one voxel here and looking at it across time, but I'm looking at how its grayscale value goes up or down, so white and black, instead of going up and down physically in a plot. And so I don't know exactly where every voxel is in space, but I'm just trying to see, are there any global patterns? And indeed, at a given point in time, sometimes I see a big set of up and down changes in the time series in the sense of the voxel value is kind of moving to white or black in this grayscale measurement of change. And if I jump back and forth between these two slides a little bit, actually what I've done is I put the start and end of the time series, I've locked them together. And if you notice, when is there the greatest change across a lot of voxels, whether it's a big jump up or down in terms of changing to black or white, it's at this time point where there's a lot of up or down change in my motion parameters. This is all to say that this is a consistent way of looking at things. Where my motion parameter is changing a lot is where I get a lot of subject motion, which is where I get a lot of jumps in my time series, as shown here in kind of grayscale. Okay, so however you want to look at motion, these are ways you can all say, yes, the person was moving a lot here, the subject was not moving a lot out here. In the same way, the parameter might be non-zero here, but it's pretty constant. There's not a lot of motion here. The time series is fairly constant across here. Okay, these are pictures, which are great, but we need a little bit more of the mathematics of it. When we have our 6 rotation and translation parameters, that's great, but we want like a single omnibus measure of how much was the person moving here, do we think? And so what we do is we take these 6 time series, and as we said, it's the change in them that is telling us when the person is moving. So what we do is we calculate E norm, which is the change in each parameter, the delta of dp and the delta of dl. So how much the translation along the anterior post axis is changing, left-right axis is changing. We take the square root of the sum of squares of that. And we make a single time series out of it. So we're calculating this at time point 1, how much was it changing at time point 2, at time point 3, and we get a history of how much as an omnibus single measure this was changing. We call that E norm. It's the Euclidean norm of the motion parameters. Square root of sum of squares is how distances is calculated. Physicists in the crowd might be yelling at me right now that I'm adding squared millimeters with squared degrees, and those have different units. You're correct to yell at me, but I'm saved slightly by the fact that the human head size makes it a good approximation that 1 degree rotation at the edge is about 1 millimeter of change. So I'm kind of fudging this equation a little bit, but I'm giving these all kind of equivalent or approximately millimeter units here. So I usually write that E norm has units of approximately millimeters, which is a pretty good approximation for a human head. This is a more sensitive degree motion trace than something like if you just took the absolute value of these and added them up. That's what the FD quantity is. Any individual motion parameter sticks out more, so we don't wash out motion that occurs in just 1 degree or 1 axis. Another thing to note is this E norm is going to be our omnibus measure of motion. We are going to use this to threshold where we might have too much motion to analyze data at that time. Since E-norm is a difference of two time points, whenever we censor based on E-norm, we're going to remove two volumes from our analysis. So if there was large motion between volume 11 and volume 12, we don't know which one had the biggest amount of motion, and in reality, they probably both did because human motion is not absolutely instantaneous. Both of those volumes would be censored. The way that the 3D Volreg output is used to calculate enorm is this 1D tool function here. And I'll just mention that we also have another quantity that we use to judge for did the person move a lot at this time point. When we use AFNI-Proc, we look at the outliers or the relative fraction of outliers occurring at a given time point. So what we do is we take the EPI volume mask, and at time point, let's say 7, we calculate how full that mask is with outliers at that time point across all the voxels in it. If that fraction is large, we're going to say we don't trust that volume because the person was probably moving. What is large? We usually say if an approximate mask has 5% outliers or more, we will censor it. Excuse me. And to show this kind of in action, like how we'll look at it in the quality control tomorrow, across our time here now, so if I go back to this image of 0 and moving here, this is what our enorm trace looks like across time. So there was a time point of a large amount of motion here. And what we do is we set sensor thresholds for the enorm value. So where the millimeter, approximate kind of quasi-millimeter was more than 0.2, then we're going to censor out those time points. And the outlier fraction is shown here. And you can see that sometimes where there is big motion, we see the big outlier fraction. It's not always and every time. These are independent measures, and we kind of take the union of what they would tell us to censor. In this case, the outlier fraction is just a subset of when we would have censored based on enorm, but we use these both independently. And these just show the distributions across all of them in case we cared about that. So the red highlights where we'd censor because one of these traces was above its threshold. Okay, I will take a break here for our 10-minute break now. We can break for our full 10 minutes. That's okay. So we'll come back at 4:23. I will pause the recording. All right, slide from current slide. All right, so we've been talking about motion and estimating motion, and then this idea of we can kind of try to binarize motion and say, well, there were problematic points here that I don't trust, and so I'll censor those. How do we define what the threshold is? It's extremely tricky. We'll talk about this a little bit too. There is a hands-on aspect that we have in the AFNI handouts. We can copy and paste some and look at some motion. Maybe we'll come back to this if I stay okay on time. I want to talk about some caveats of motion. So we talk about we use the term motion correction. That inherently implies that we are actually correcting motion, and that is a dangerous thing to say. So motion adjustment or motion amelioration would hopefully be better terms, but anyways, we use the fully loaded one that we probably shouldn't. There is no way we can make our data look as if there was no motion there. Whenever we do motion correction, it's an alignment process and there's regridding. So we're mapping data across space. That's a smoothing process. So for one, your data is going to get blurred just by doing motion correction. Another thing is we have to make sure that the data is actually being corrected. If we look at this example here, so this is a macaque data set that had a task that was involving, I think, sipping juice at stimulus time. And so if you see here, the brain is moving around, and we can see just visually the brain moves up and down and kind of back and forth. And in the time series, there's some spikiness associated with it. If you run 3D Volreg on this, actually, when you look at this volume here, this movie, it looks frighteningly similar to this one, where I still see a fair amount of motion visually, and the time series still has these bumps. Did 3D Volreg just fail? Should we not use AFNI? That's not the case, actually. You should use AFNI. The the point is that 3D Volrig ran on everything in the field of view, including the non-brain stuff. And macaques have very large jaw muscles that move around. And so this whole thing was aligned over time. If we mask out the brain and remove these jaw muscles and the non-brain parts, then look at the job that 3D Volreg did. Actually, you can see that there's very little motion here, and some of the bumps and wiggles went away. So a couple lessons here are when you're doing things where there's a lot more than just brain in the field of view, you have to be careful about what's being aligned. When you have a stimulus design, if your stimulus involves sipping juice, and you have big, powerful jaw muscles in your subject, then you're going to have probably task stimulus correlated motion. So even if we get rid of some spikes and things, we might get rid of signal as well and cause other problems. Another thing is we always have to look at our result. Just because the program told us that we got rid of all motion, there might still be some motion effects for various reasons. The spikes, as we've seen, go up and down, or baseline changes go up and down in very unpredictable ways as well. So it's really tricky to have motion. The best thing to do is to not have any motion at all. So making your experimental design as careful as possible and preparing your subjects as much, whether it's taking kids and using a practice scanner so they're less nervous, so they have a better sense of what they're doing, designing your studies so that the expected amount of motion is small, is always going to be better than trying to correct it later. Motion is really tricky because it occurs on slices, not volumes. And just regressing out motion is really hard because the spikes go up or down unpredictably across different parts of the brain. So the motion will be dealt with in different ways by definition. Censoring is one thing that we do. It's also called scrubbing in some software tools. It's really just trying to sweep under the mat that we have motion. Usually we're not censoring all the volumes out that have motion in them, especially sometimes if they're large sweeping motions of the head. There'll be occasional moments where there's still motion, but it doesn't look like it from a motion parameter point of view. It can really be tricky to deal with as well, and there's feedback into the magnetic field. If your groups have different kinds of motion, you want to make sure that you're not just interpreting the fact that you censored one data set more heavily than another, or that some bold response looks larger, but it's really got more motion in it, something like that. So if you're studying, Parkinson's versus healthy control subjects, you really need to make sure that the motion differences that are expected between the groups aren't the thing that you're measuring rather than neuronal differences. That is extremely hard when you have patient populations that are more predicted to move. So, and we looked at some things we can look for hallmarks of motion when there might be problems as well. So these are all things to be aware of. There's another case where we can use EPI alignment. This is a particular case where you've acquired a few volumes that have reverse phase encode data sets. So one of the geometric distortions that I mentioned the EPI data sets have is particularly along one axis, the phase encode axis, which in practice tends to be along the anterior posterior axis. So the brain can get preferentially stretched out or squashed along part of the axis. If you acquire a reference volume, just a few EPI volumes with opposite phase encoding, you can use that because they will be, if this original data is squashed here and stretched here, if I acquire data with reverse phase encoding, it is squashed on the opposite side and stretched here, and I can use those two different distortions to kind of average out and calculate an intermediate data set. So through working with Vinay Rupchan Singh, we worked to implement a program in AFNI called EPI B0 correct to do this kind of EPI distortion correction. You can include that in your AFNI-Proc processing. So this is the name of the program here. This just shows relative to an anatomical data set where the edges of the anatomical are here. If you have an uncorrected EPI, these are the same edges moved over. You can see the EPI sticks out here and is squashed, but after correcting with this program, the data is much more geometrically put back. Note that it's very difficult to undo the squashing aspect because time series have been mushed together. So even if we stretch them out to the correct place, there might still not be corrected as well. So there is even a difference between whether you're on the stretchy side or the squashed side still, but geometrically things are in better shape. Okay, this is just a summary slide of everything I've said so far. One thing we haven't talked about is global signal regression, which is something pretty good for resting state processing. There's been a lot of ink spilled on this, and people tend to just be either in one camp of doing it or not. In general, we really don't recommend it, and we have a kind of a lot of papers about why not and different other groups that have looked at this as well. So you can read those if you're interested in that. But the main thing is design your study carefully. That is by far and away the best thing you can do for motion correction versus all these other things that we've talked about. You can really introduce biases in different ways with having a lot of motion around. Okay, let's talk about EPI anatomical alignment, a different case of alignment. Here, we're going to use primarily line EPI in nat.py and often in AFNI-Proc. And this is going to do, instead of rigid body alignment, linear affine alignment. We're going to assume the data isn't hugely distorted in this case, but the EPI might be a little bit distorted relative to the anatomical. As I mentioned before, the main cost function we're going to use, because the tissue contrasts are opposite in this case between the EPI and the anatomical, is LPC or LPC plus ZZ. All right. Let's see. So there are various strategies that we have. So in the good old days of converting data sets, often the coordinates tended to be pretty terrible and not really reliable from the original scanner. So that even if the data sets came from the same session, the EPI and the anatomical weren't always well aligned. For that reason, we often had as default kind of doing a center of mass alignment between the two data sets. So these options of big move and ginormous move have that. Sometimes also your data set has really terrible tissue contrast. When people pump up the flip angle thinking it gives them higher signal to noise ratio, even though it really doesn't, above like 50 or so, what happens is you really lose a lot of tissue contrast. And in this case, the LPC plus ZZ might not be so useful anymore. So the one we might fall back on is like NMI. Anyway, you can ask on the message board for different cases where alignment isn't working well. There's all sorts of cases where people might have data sets with like stroke or lesions or dropout in different cases, different species, and very different types of data. Please ask on the message board. Daniel Glenn in particular in the group has done a lot of work with different clinical cases and different things like that. We have in the AFNI-Proc commands kind of general sets of options we start with. But again, the idea with commands that we put out there is it's a vanilla mode. And if something's not working, we can work to change an option and improve it for your data, your study of interest. Also, make sure that when you look at your data, you're judging the correct things. If you take a look at how these two data sets overlap and you think, oh my goodness, my alignment is terrible, you might be ignoring the fact that the anatomical data set whose edges you see here and this EPI data set behind it, whose edge you see sticking out here, that actually the EPI, the real brain edge is here, and this is CSF sticking out, that's the bright stuff. So you have to make sure that you know actually the alignment of the edges of the gray matter of the EPI here actually do align pretty well here. In most cases, as we've looked at it a few different ways, we like to look at the edges of one data set over another. And this is what the quality control does. There are different programs that do it. Many of the alignment programs like SS Warper will output quality control images for you automatically. And actually, SS Warper, because it works progressively, puts out a series of images. So if we need to troubleshoot it, you can take a look at those or you can send those in so we can see at what stage it's falling apart. But this balances being able to see the features and how well they align and things like that. Daniel walked us through a lot of different ways of overlaying and underlaying data, looking at things in the GUI, turning on edges and things like that. So this is just a review of some of those points. There's a add edge option for Align API in that, so you can accentuate edges in the overlay, but we also have the different adjunct edgy align program too. This is just an example of using it, and then you can run, it creates a script called at add edge that you can use to visualize the results. It drives the GUI to show you the data interactively. Another thing that we use alignment for and visualization of alignment and why it's also important is to check for what we call left-right flipping. If this is an anatomical data set and this is the same person's EPIs here, which one of these do you think actually has the correct left with the left and the right with here? Is it this one or this one? I will let you decide. Okay, let's vote 3, 2, 1. Who thinks it's the upper one? Who thinks it's the lower one? To be honest, I don't know, and I wouldn't trust myself necessarily just by looking at these. I would want to judge it. And the way we can do it is we can use alignment to tell us, because the human cortex is not very symmetric, or not extremely symmetric, I'll say, in terms of left and right. When it's correct, we can see the sulcal and gyral features lined up very well everywhere in the cortical part. And when it's not, we can actually see that the sulcal and gyral patterns don't really match, even if they appear to be, very symmetric to the eye like this. At the level of detail that we want to look at alignment, they're not. And this is actually important because something we found in a lot of public data sets is that actually the EPI and the anatomical appear to be left-right flipped. So we don't know which one's right. We don't know whether the anatomical was flipped or the EPI was flipped, but left and right were misdefined in one of them. And this probably goes back to something with the DICOM conversion or some kind of header mistake, and that's okay. But we basically noticed this because in general, when we looked at the quality of EPI anatomical alignment, for some data sets, it just wasn't very good, and we couldn't understand until we tried flipping it, and that solved it. And so it was kind of systematic across data sets. So this does not tell absolutely what's left and right. When we run into this problem, like I said, we don't know which one is correct and wrong, so we just probably can't trust this data set overall, which is unfortunate, but at least we knew that we couldn't trust the data, which is why we checked for this. It's kind of surprising how many data sets have this, which is why we put this in our AFNI proc by default now. Dealing with data is really hard, and you get surprising things happening. So this is a paper about it. Actually, I guess it's no longer just a preprint. The full paper has been out for a while, looking at surprisingly common left-right flips. So the AFNI proc quality control, if you use this option when you process, will warn you about it and show you images so you can check and verify what it's judging based on the cost functions. All right, and now let's look at aligning the anatomical data set to the template data set. This is really the work of 3D QWarp and AFNI, and then we have these different wrappers or different variations of it that we've developed over time. The SS Warper variety, and now SS Warper 2, actually combines the nonlinear alignment with skull stripping. So basically, if you could remove the skull from your data, nonlinear alignment would be a lot easier. But if you did nonlinear alignment, you could use how you aligned your data to a template to punch away the skull and non-brain material. And what this program does is it toggles back and forth between those two jobs simultaneously to try to improve both of them all at once. So that's the SS is for skull stripping and nonlinear alignment, the warping. There's an equivalent for this with animals called @animal warper that does the same thing. It also does some mapping back and forth of ROIs and does some surface generation. And both of these can be combined with AFNIPROC very easily, where you estimate the nonlinear warps before you do AFNIPROC, and then you hand over the warps to AFNIPROC so that when you reprocess your data at some point or change an option, you don't have to redo nonlinear alignment either. Nonlinear warping is fairly slow because it has this local patch refinement and smaller patches as it layers through in more detail, but it's inherently parallelized for better processing speed. So when you run this on an HPC or on a computer, having multiple threads is good. You can control the number of threads for parallelized programs in AFNI by setting an environment variable called ompnum threads, because it's OpenMP that we use to do this. So this is just an example. I don't know that I would set it to 7. I'd probably set it to a multiple of 4 or something like that. But just as an example. Now, of course, if you set it to 7 and you only have 4 CPUs, you're not going to magically get more CPUs. So it's limited by the amount of that you have on your computer. All right. Some rules when you're doing things with templates and registration. You really want to pick something that's relevant for your data set. And anymore nowadays, we've had a little discussion about the Taylor Act template specifically. There are so many templates. You can choose something that's appropriate for your age group, certainly your species. There are even ones that are kind of by geographical region that may be more relevant. And it's good to use something that is going to be as close as possible for your data, so the least amount of warping that you need to incur is kind of there, or the best amount of alignment with the most detail. You also want to use something that's not a blurry template. Sometimes I see, even nowadays, like these oddly blurry templates without very good tissue contrast between gray and white. And you really want something that has sharp features in it so that even if your data isn't the greatest quality or doesn't have the sharpest features, you want to give it the best chance to align to something as possible, because the nonlinear algorithms across a lot of software are very powerful nowadays. So, treat yourself right and use a data set that has good tissue contrast. Let's see. And normally we have a whole presentation on template atlases. I don't think we have time for that in this boot camp, but I'll send the link for it, and it's on the YouTube channel as well. The SS Warper, as I mentioned, or again now SS Warper 2, I have to update this. Anyways, does this job of both skull stripping and doing alignment, and it makes QC images as it goes to help you judge both the masking and the alignment job. How do we judge alignment? Well, one thing we can do is we can take a look at warping a particular region and seeing how much it overlaps when that region has been defined across different subjects. So, for example, looking at like ants, the Dartel, FNIRT, and 3D warp. In this case, we're just looking at the fraction of overlap across the masks of these regions. So where you see yellow and orange is better. I see some yellow and orange here and here. That's good. I see a lot here. That's also quite good. So, anyways, whatever your software you're using, you should be using nonlinear alignment to a template space. In the bootcamp, we will use affine alignment only, but that's just because of time considerations for processing in class. For any real analysis, we will use the powerful 3D warp for that, which again performs quite well. There are other kinds of alignment that you can do in AFNI. So we're focused mostly on fMRI and EPI data here, but we in particular, in this case, this is working with Justin even before he joined the group, and Daniel for a long time have worked on all sorts of different modalities, a lot of clinical applications, DBS electrodes, using CT. Certainly we do a lot with diffusion data, PET, and things like that. We have different ways to visualize it. Data sets that have tumors in them, we have different masks that you can include and exclude things with. So again, by all means ask. We may have some existing functionality or experience with doing these things. It's an ECOG example. And again, the main thing is to make sure you kind of check these things out and find an appropriate cost function that's maybe the trick is you do some kind of non-standard data. This is not actually a movie. It's not frozen. And this is the a little bit with using the Animal Warper program. So not only does it do alignment, but it will map atlas regions back into native space where many people do more alignment in subject-specific space in animal studies than in human studies. And so this program helps with that in particular. And again, we try to put out QC images now with some of these wrapper programs, and those are helpful. All right. So the main thing is, if you remember nothing else from this afternoon, that you should always, always, always look at your results visually when you're judging alignment because the program did what it could computationally. Now it's up to you as the human eye to look at it and say, oh, yep, there we go, or oh no, this isn't there. And you may have to focus on different parts of the brain. You may only expect a given quality of alignment. If your EPI is very distorted, there's only so much affine registration or anything it's going to do to put your data where it should get put. Also, even for nonlinear alignment, sulcal and gyral features differ across subjects and between subject and a template. So really have these things in mind and use that to be discreet with your interpretations to not overinterpret misalignment or just heterogeneity of features across subjects. And we try to talk about different programs and different ways that you can systematize the images as well. So you can do alignment and use Chauffeur to check it for you. Programs like SS Warper, Animal Warper, they will actually be using Chauffeur for you already, but you can use it for other things too. All right. And we will be looking at AFNI-Proc tomorrow a fair amount and what it does with alignment and different option usages. All right. Oh, here's just some chauffeur commands for combining with the image concatenation as well. So anyways, users can look at that. Are there questions on what we've covered here so far? I think the motion stuff is probably maybe the most conceptually challenging because we have to deal with the time and the derivatives of the motion and this and that. So maybe since we do have a little time, for those who are gluttons for punishment, we can go back and look at the EPI hands-on case here. So this is in the PDF, just a little bit about what we'll do very quickly and look at. Copying and pasting from PDFs is not good because subtle things like this minus sign might not actually be a real ASCII dash. So I'm going to AFNI open with a text editor, AFNI 14 commands alignment.txt. All right, and you can follow along with this too. What we're going to do is we're going to copy, paste some commands, and then look at some things. And this is all related to the motion using 3D volreg. And the slides have more kind of notes on it, so I'm just going to move that over to the side. So I opened up, again, AFNI 14 commands alignment.txt. And now I can copy and paste into the terminal, and I'm going to go back to the AFNI data 6 directory with that first option there. And the first command that we're going to run here is we're going to run 3D volreg on this EPI data set. You know what? I'm going to make this slightly larger. There. All right. Hopefully people can read this. And we're going to output it to an EPI. So this is run one, and we're going to give it, this is the volreg time series out that's been corrected. We're also going to save out. We're not just going to correct the data set and get a new data set where the volumes are put back in place. We're going to save out what were the registration parameters all across time that accomplish that, which will actually be the history of the motion then. And we're going to save that as both a matrix and as a 1D file. And then in this case, we are choosing just the third volume, so index 3 volume as our reference time point for motion correction. As I said earlier, in AFNIPROC, we would specify the min outlier data set. In this case, we just haven't calculated the min outlier in this example, but AFNIPROC would. So I am going to copy this and paste it, and it's away and running. And I can look at the number of volumes, I believe. Oh, okay, so it's even done already, which is great. I'm going to 3D info, the number of volumes in EPI run 1. There are 152 volumes here. So it finished that in about, I don't know, a few seconds is how long it took to run. And now it has, if I do ls-ltr in the terminal, it's showing all the outputs in my terminal, everything here, but in a long list and time reversed. So these are the data sets that it just created now at 4:53 p.m. So it made the matrix that I asked it to. This is the output data set that's corrected, and this is this D file volreg 1D. We already said 1D files are just columns or rows of numbers. Let's take a look at one of these files with this 1D plot command. Okay, so this D file VR, I'm just copying and pasting that here, and 1D plot shows me that. There are a couple options there. So it says 1D plot for this file. We know that it came from 3D volreg, so there's a special volreg option, so it knows how to label things, the order of the columns. And sep scale means that my y-axis isn't glued together to be the same min and max across all my 6 rows. So if I look here, this is my estimation of motion across time. This is actually the same data set we looked at earlier where there was, excuse me, one big nodding motion at time. So this is the time axis. So at about time 44, 45, it tells me here, this is the delta AP, delta right, left, inferior, superior, yaw, pitch, and roll. Okay, so these are my motion parameters plotted out for me. If I just quickly cat that D file, it's just simply 6 columns of numbers, and that's what's been plotted here. Ta-da! Is there any special thing here? If I look at just the first few numbers here, the head command shows me, I think, the first 10 rows by default. Do you notice anything particular about any row of numbers here when we're looking at these 6 motion parameters? So this is, I don't know, delta, AP, right, left, inferior. Looking at numbers isn't always the most fun thing, but actually one row pops out at me, this one. This one is all zeros because it's row 0, 1, 2, 3. And if you remember, I said use the third volume, index 3 volume as my reference. So when I align the reference to itself, it doesn't have to move very far in translation or rotation. 0 millimeters and 0 degrees. Everything else had some non-zero. Okay, this is just kind of making sense of what's here. And if we want to, okay, we mentioned this term E-norm, the Euclidean norm. So these are my 6 motion parameters across time. Let me calculate that omnibus measure of them, the Euclidean norm, like this. And I'm going to put in here a sensor value of 0.3. I'm going to copy and paste that. Ta-da, it's done. It even tells me that the total number of censored volumes was 6. And now I can do a 1D plot command on the output there, which has some special functionality that we won't go in with, but trust us, it works. Here we go. This is the enorm with profile with basically we were telling it there's 152 time points and put in a red line at our sensor threshold of 0.3. That's that funky syntax there. So we can see where the censoring is going to happen. This is a very simple, quick plot. This is not what I would publish. Even the QC does a fancier one, but this is something kind of at our fingertips that we can really look at the data quickly and see that it makes sense. Indeed, if I line up a little bit the start and finish of these plots, life is too hard. So here, where was there big motion? It's kind of at this time point. Yeah, that probably lines up well that things are being calculated correctly. All right, and if I want to see, oh yeah, now what I save out is where is there censoring that's happened. If I cat this text file, so now let me just list things out again. I've made now these sub-censor things. If I cat out one of them, there's a censor string. So this is the AFNI syntax. If you remember uh, way back earlier where we talked about subbrick selection, so volumes 43 dot dot 45. So 43, 44, and 45 are censored, and so are 60, 61, and 62. So anyways, this is just kind of showing you some things that are output. And if you want to view something very fancy here, we can view 1D plot like this, where not only are we showing the plot, the sensor threshold, but we use that the kind of string information that's stored here to show where they're censoring. Again, even this is very simple, but this kind of gets at the point of highlighting things visually. And we'll see in the AFNI Proc QC tomorrow, there'll be a nicer looking version of this with some more features around it. But anyways, the main thing is understanding 3D volreg and what it does, the motion parameters, turning those into enorm, and then that's a single number across time that we can censor and then highlight some time points there. All right, and I have 1 minute for questions if anyone has a question. Why does it say one? Yeah, so the one, it's basically, I think this is a sensor time series. So if you're asking the question, which time point should I censor? You imagine everything is a zero except where it's one, that's where it would be censored. So I think it's referring to that it's like censoring is on for these time points and it's on for this time point. It's kind of a syntax thing, and the programs are built to use that option, but I think that's the logic of it. Let's see, the new tool on distortion correction, is that the EPI B01, the reverse phase encoding one, Alexandra? Yes. Um, let's see. Sure, I'm not sure what more to say other than it exists, and there are two ways you can do phase distortion correction for EPI volumes. You can acquire what's called a phase map, which is basically something that, as it gets further away from zero, is telling you where there was more EPI distortion. And you can actually use that as kind of a warp field directly. Or you can use a reverse phase encoded data set and estimate the difference between warped in one direction and warped in the other direction. You take the kind of average and hope that averages out to be not warped. So both of those methods of correcting EPI volumes rely on doing a little extra acquisition at the scanner. If you don't have those, you can't use them. In practice, we usually have found that the reverse phase encoded form tends to work better, and that was using both AFNI and FSL's version of it, whose name I forget now. Top up, thank you. And anyway, in both cases, the reverse phase encode worked a little better. That's nice because you don't need a whole other time series. You just need a few volumes. Like maybe we usually tell people to acquire 5 or 10, which is something like 10 to 20 seconds of an extra scan. Why do you acquire several? Mostly just in case the subject moves, you don't lose all of them. And both are doable. Yes, if you have the phase data, then you can use um, EPI B0 correct.py is the program you would use on a phase data set, and you just have to translate it into being a warp. And whether you have Siemens data or GE, there are slightly different rules, and that's discussed in the help. And if you have the reverse and phase encoded one, then you use 3D Q warp dash, what is it? Something plus minus. That's what it is, plus minus. But actually, you just let AFNIPROC do it for you. You just say that you have reverse and phase encoded data set, and AFNIPROC will concatenate it. And is there a way to correct distortions and motion at once in AFNI? What you do is you correct them separately, but you concatenate the transforms, and AFNIPROC will do that for you. Oh, and I see. Okay, Brain Voyager has a tool called doing this called COPE. Interpolating time series between censored time points. So in AFNI, we do not interpolate the time series between censored time points. Once they're censored, they are censored. So we don't trust anything there, and we don't try to interpolate them because, if someone is doing a task, you don't know what happened there, especially when you have like a large set. If you have 5 time points censored, you don't really know what happened in there. So yeah, we censor and censor it out. Alexander, so for the field map versus opposite phases. There's a paper. So let's see. Oops. Thank you, AdBlock Plus, for working hard here. This is a draft about it. So that's using both the AFNI and FSL and looking at both phase distortion, like the phase map and the reverse phase encode. Both of them help you. Whatever software you're doing, do one of them. In practice, it just seemed to be that the EPI phase, the reverse phase encode, did a little bit better. But yeah, it's definitely worth doing one of them. Excellent questions. Okay, now there are a couple other programs for distortion. Um, for the question, is it better to do anterior to posterior or posterior to anterior phase distortion? This gets into the issue of you have to decide based on your study. If you are studying the visual cortex, I think you want to be careful not to squash the data in the visual cortex. So that kind of distortion is worse for you because you can't unsquash. So in that case, I think you would want to do anterior to posterior because then your anterior is squashed and your posterior gets stretched out, and it's a little bit probably less distortion-y to undo stretching than squashing. If you are studying part of the brain, in the anterior part, then you don't want to squash that. So your answer is going to depend on what your study is. Motion or distortion correction first. I I think we do the motion estimation. Uh-oh, now I have to remember
Uh,
where is the
I
blip?
think we do distortion first.
I guess the blip distortion is done. Yeah, so the EPI distortion is done first, then the motion
It's kind of
correction.
independent, but uh,
Yeah,
they're two separate calculations, really.
yeah. We can check that in an AFNI proc script to be sure. But if both Daniel and I half remember it that way, then surely it must be at least
We
at
can
least
meet in
20, at
the
least 25% correct.
we can
Yeah,
meet in the middle, right?
perfect. Yeah.
I wanted to add one thing. I think in the question about which one is correct about the flip, uh, left, right, or the top or the bottom, I think it was the bottom one that was the lower one was correct. Is that the way you remember this?
Well, the main thing is I don't want to remember.
Yes.
I want to have the check. So that's
Yes,
the
that was
point.
the main point.
I intentionally don't remember, so I don't want to fool myself into a
Right. And
mistake.
the other important point is that that was initially discovered by an AFNI user in one particular data set, and that is just and the result is a script that quantifies it to
Mm.
make it more automated. And so what we've done today is we've given you the tools to find problems. These kinds of visualization is critical for that. And so all of you are now scouts for problems. So that's an important part of that.
And I think it's worth noting as well that a lot of the things that we talk about here, they kind of come up or different options or functionality because users asked questions that something didn't make sense and they just wanted to check or just like, does this seem right? There was a gut feeling or whatever. So, on the message board, whatever email, dropping by, doing these things and kind of asking questions is just really useful because it may not be anything. It may be as good as it gets and unfixable, but there may be something that's there too. So, try to emphasize thinking critically and don't just kind of trust your data or don't just trust any algorithm. Even AFNIs, look at it and think about what it should be and all of that. What if the skull stripping is not good? Yeah, if the skull stripping is not good, it can present a challenge. Sometimes if the skull stripping isn't good for affine alignment, it might not affect too much because that's a global fit. If the skull stripping is not good and you're doing nonlinear alignment, now that becomes much more of a problem. That being said, if you're if you're off by a voxel or so in your nonlinear alignment or your skull stripping between the anatomical and template, usually your EPI resolution is so much lower, it might not matter so much in practice. So there's a lot of case sensitivity to some of the answers of these things, rather than necessarily a generality. One thing we'll mention again and again, you should acquire a little bit of data, look at it, and see if it's giving you, if you have the tissue contrast you want, if it's all these things before you acquire 200 subjects and then realize an acquisition parameter wasn't ideal. Um, so, Farouk, yeah, nonlinear warps can be concatenated with linear and affine transforms, sure. Yeah. So 3DQ warp, for example, inherently does that because it will do an affine and then refine it with nonlinear, and you can glue those together. You can glue in other affines. You can glue in multiple nonlinear warps. Yeah, things just get a little slower depending on the what's concatenated, what's being done. Let's see, Jonathan, for your question, can 3D QWARP use two volumes of spin echo EPI, one in APPA, or does it have to be the same fMRI gradient echo? I just give it a try. If it's a little bit of an empirical question, so how flexible can the 3D QWARP plus minus be to other types of echoes? You probably want it to be things that have similar contrast. I don't think it has to be both like gradient echo and that, but yeah, I would just kind of try it as long as the AP and PA look kind of similar. Yeah. What's the worst that could happen? All right. I guess, okay, we've kept recording all this. Okay, so I will stop this. If people have more questions, these are all really excellent. I know it's late and a long day for many people here. Thanks for sticking with it and thinking critically through all this stuff. And yeah, by all means, you can email us questions, talk about them tomorrow, all that, write them down, and yeah, just let us know.